Okay, so here we are, section 4.3, part 2, and we're to example 2, where typically in the class we'll pick one of these problems. But I'm just going to go with the first one because I want us to get the techniques down and not get bogged down in details about trigonometry. So we'll pick this first problem, and they want us to figure out where find the intervals on which the function is increasing or decreasing. Remember, the function is increasing where the derivative is positive, decreasing where the derivative is negative, and find the local maximum and minimum values. So you go with this first problem. So the first thing we need to do is figure out where the derivative is 0. So we can take the derivative, and we will get 12x squared plus 6x minus 6. We set that equal to 0. And since it's equal to 0, we could divide each side by 6, which would then give us 2x squared plus x minus 1 equals 0. And it's a second degree equation, right? So we know for sure we can solve this, because if it doesn't factor, we could use a quadratic formula because it's a second degree equation. But in this case, this one will factor. So we can factor it. And we could go 2x and x, 1 and 1, and make this a plus and a minus. So we'll get outside is 2x, inside is minus x. Okay, so that should work. So then we know that we've got something times something equals 0. That means that it could be this equals 0 or that equals 0. So we could have that 2x minus 1 equals 0 or x plus 1 equals 0. In this case, 2x equals 1 or x equals 1/2. In this case, x equals negative 1/2. So we get two critical numbers. Right, so these are our critical numbers. We don't have to worry about where the derivative doesn't exist, because if you look at the derivative, this derivative is a polynomial. Polynomials exist everywhere. There's nothing you could plug in for x to make this not exist. So we get these two critical numbers, and then we basically finish this problem the same way we did before, where we're going to take a number line and divide it based on these critical numbers. So we take a number line and we divide it up at negative 1 and 1/2. So we pick some test points. So I'll pick negative 2, 0, and 1. And then we've got our derivative up here. I mean, this is our derivative, but it'll be easier just to use this, because all we really need to do is figure out, when we plug in these test points, is the derivative positive or negative? So one thing you could do is take negative 2 and plug it in up here. It's a lot of calculations. It's much easier just to use this, because we don't really care what the answer is. We just need to know if it's going to be a positive or negative. So even though this derivative isn't really the same as this, because we divided a 6 out, but if you put the 6 back here, it doesn't change whether or not it's positive or negative. So what I'm going to do is do kind of like we did before. I'm going to put over here, I'm going to have, well, okay, so let's just put the whole derivative. 6 times 2x minus 1 times x plus 1. So this is our derivative, because if I multiply this all, if I FOIL here and then distribute the 6 through, we'll get right back here to our derivative. So then, with this being our derivative, we can pick our test points negative 2, 0, and 1. And we basically just have to do this. because this doesn't change whether it's positive or negative, so I don't really need to put the 6 out in front. All I need to do is take this -2, I'm going to plug it in here and see if we get positive or negative. So if I put a -2 here, I'm going to get a negative answer, right? 2 times -2 is a negative, then subtract the 1, it's still negative. So this is going to be a negative, and then if you plug a -2 in here, you get another negative, because -2 plus 1 is a -1, so that's also negative. So negative times negative is a positive. So on this interval right here, on this interval, this was our test point. We could have picked any point on this interval. We would have gotten the same thing, a positive value. So we can say that on this interval, the derivative is positive. That means the function itself, f, is increasing on that interval. Now when we get to -1, the derivative is 0 here, so that it flattens out. And then to see what it does on this interval, we pick a test point. I picked 0 because it's easy. You could have picked 1/8 if you want to, just any number in between here will work. And then you plug it in over here again. So when you plug a 0 in here, we're going to get a negative here. You get a positive here. Negative times positive is a negative, so it's less than 0. So on this interval, the derivative is negative, which means that the function is decreasing on this interval. Then we go to this last interval, and we pick a 1. And remember, I could pick a 7 or a 10 or any number you want, because whatever this derivative is doing at 1, if it's positive at 1, it's going to be positive forever, because it can't turn to negative without hitting 0 first, and there's no other zeros. The derivative is only 0 here and here. So to figure out this last one, I plug in 1 here. If I plug a 1 here, I'm going to get a positive number here. Plug a 1 here, I get another positive. So we get positive times positive, which is a positive greater than 0, which means the derivative is greater than 0 here, which means the function is increasing here. So then from this point, we can use our first derivative test, because we've got the function is increasing here and then it's decreasing. So think of it like this: the function's increasing, right? It's going up, then it flattens out at -1, then it decreases. So it's doing this kind of shape, right? So it's got a peak here, it's got a local maximum here. So by the first derivative test, there's a local maximum here. Local max at x equals -1. To figure out the local max, we have to plug that in. So the local max is f of -1. So again, we put the -1, plug it in the original function, right? This is going to the original function, goes back in here, not in the derivative, goes in the original function. So when we plug it back in the original function, we get 6. So the local max is 6. And then over here, we've got the function is decreasing, then it increases. So it's decreasing, getting lower, lower, lower. Flattens out at 1/2, then it increases, right? So it's decreasing, function decreasing, flattens out, increases. So that means we've got to be having a minimum here. Again, by the first derivative test, we have a local minimum at x equals 1/2. The local minimum is f of 1/2. If you plug in 1/2 in the original function, you get -3/4. So we could say, to answer the question, there's a local max here. So local min here. But they also asked us about where the function increases or decreases. So looking at here, we can see the function's increasing on this interval and also on this interval. So we can say that f increases on negative infinity to negative 1, and also, or you could put a comma, however you want to do this, 1/2 to infinity. So the function is increasing on these two intervals from negative infinity to negative 1, and then from 1/2 to infinity. And it decreases on this interval right here between negative 1 and 1/2. So that's kind of a typical problem that you'll see in this section. So let's move on here and talk about asymptotes. So with these asymptotes, we've got, well, basically first remember that these are lines, right? These are lines. Asymptotes are lines. So they're going to be like x equals a, right? This would be a vertical asymptote. Or y equals b. This would be a horizontal asymptote. So a and b would be, of course, constants, but when you have x equals, like x equals 3, that equation is going to be a vertical line because it's saying it doesn't matter what y is, x is always 3. And also over here, same thing, if you have y equals 2/3, that's the equation of a horizontal line. So for vertical asymptotes, these occur where the denominator is 0. The denominator equals 0, and also the numerator is not equal to 0. If they're both equal to 0 at the same spot, then you've got a hole in the graph. But this is what we talked about before. To find vertical asymptotes, it's what you learned in algebra class. You have a rational expression and you set the denominator equal to 0. That's how you find the vertical asymptotes. Now horizontal asymptotes, what we did earlier is we had to take the limit as x approaches either infinity or negative infinity of the function, and that limiting value would be the horizontal asymptote. And then in algebra class, you learn something like this. In algebra class, you'd say, so let's say you've got y equals ax to the n plus ... for the numerator. Denominator is bx to the m plus ... So you got this rational expression, and you probably learned in algebra where we didn't use a limit, but we could notice some things about the powers up here. And in algebra, you may have just had to look at these powers to go to your conclusions. Now, the conclusions are true because of calculus, because when you take the limits, you'll get what is suggested in your algebra classes. So you would have learned something like this: when n is greater than m. So this power here, when it's greater than this power here, when that happens, that implies that there is no horizontal asymptote. And you would see that if you took the limit, you'd get, if this power is bigger than this power, in the long term, this numerator will dominate the denominator and you'll get some sort of infinity there. So there'd be no horizontal asymptote. And then if n equals m, so if these powers are the same, you'll get a horizontal asymptote. You'll get y equals a over b. So it'd be, the horizontal asymptote would be these lead coefficients. And then another thing that could happen is if n is less than m, then the denominator would dominate and it would send this whole thing to 0. So in that case, if n is less than m, we have a horizontal asymptote of y equals 0. So the reason I mention this again is some of the homework in this section will ask about these asymptotes. So this is just a little review of what we said before. Okay, so now we're going to talk about what the second derivative says about the function itself. So now we're looking at f double prime of x. What does f double prime of x say about f of x? What does the second derivative say about the function itself? And here we need some pictures. So let me do this here for number 1. Let's see, where's number 2 at here? Okay, there we go. All right, I'll try to draw a little smaller here. Let's do it like this. So we need to make a couple of graphs here. Couple of graphs like this. And I'm just going to make a function. So let's say y equals f of x goes like this. Or maybe it goes like this. And then for the second one here, again, for whatever reason, when this program I'm using opens these documents, it makes the spaces really kind of weird. So I'm just going to move the second one up here because there really shouldn't be this big of a gap. So this is actually number 2 here. And then we have these. Let's say these functions are more like a little piece of it here, or even more of the curve here. And of course these are y equals f of x. Okay. So right here it says, if the graph of f lies above all of its tangents on an interval, then it is called concave upward or concave up on the interval. So if you look at this first one, problem number 1, if I take tangents to this curve, these tangents to the curve, all the tangents are below the curve. So the graph lies above all of its tangents on this interval. This black graph, this curve is above all the tangents. The tangents to the curve are all below the curve. So in this case, this is called concave upward or concave up. So looking at this, you can see you can think of it as it opens up. And here's a really easy way to remember it. You guys are going to love this one. It opens up like a cup. Right? Opens up like a cup. Like if this were a cup holding water, it would if this curve continues, it'd be up like a cup. That's concave up. So then we have this other type of concavity where the graph of f lies below all of its tangents on an interval. So if we make the tangents on these curves, the tangents end up being above the curve. The tangent lines to the curve are above the curve. You know, these tangent lines are not all that great, but you can see that the graph lies below. The graph here is below all the tangents. When it does that, it's called concave downward or concave down. And you can see this, looking at this, it opens down. Let's see if you guys can make the prediction for this. Easy one to remember. Opens down like a frown. Some of you already knew. You could tell it was coming. Up like a cup, down like a frown. So this is leading us to what's called the second derivative test. So now that we have these pictures, I'm going to look at the words here. So I guess we're going to have to kind of go back and forth to make this work. But notice that in the graph 1, going from left to right, the slope of the tangent increases. So going from left to right, moving from left to right, the slope increases. So it's flatter here, and then these slopes get steeper, right? The curve's getting steeper. So the slope is increasing. And here, same thing. It's this slope is negative here, but it's less negative. It's getting closer to being flattened out. So these are always increasing. So f prime is increasing in this case. So when we look over here, we can see that going from left to right, the slope of the tangent line increases. This means the derivative f prime is an increasing function, right? If the slope is increasing, well, slope is the geometric equivalent of the derivative. So the derivative is an increasing function. And so if f prime is increasing, then its derivative, f double prime, is positive. Which leads us to this. When the second derivative is positive, the actual graph, when the second derivative is positive, the graph of f is concave upward. Concave up like a cup. The easy way to remember it is this. Think of when the second derivative is positive. When you're thinking positive thoughts, like when you guys first walk into class, the beginning of Calc 1, I look out there and I see a whole bunch of this. Happy faces. Everybody's thinking positive thoughts. So when you've got second derivative is positive, think of positive. When I'm feeling positive, I have a big old smile, right? Concave up like a cup when you're feeling positive. Now, on the other hand, in graph 2, going from left to right, the slope of the tangent decreases. So now going from left to right, the slope of the tangent's decreasing, right? It's positive, then it's getting flatter, it's getting closer to 0. Same thing here, it's positive, getting flatter, now it's turning negative, so the slope is decreasing there. So over here, we've got going from left to right, the slope of the tangent decreases. This means that the derivative, f prime, is a decreasing function. So if f prime is a decreasing function, right, f prime is a decreasing function, then its derivative, f double prime, must be negative. So when f double prime of x is less than 0, the graph is concave downward. Easy way to remember this. Negative. Second derivative is negative. When you're feeling negative, like, at the end of Calc 1, class is coming to an end, everybody feels a little bit sad. I look out there and I see a whole bunch of this. So when you're feeling negative, concave down like a frown. So that's kind of an easy way to remember it. And those two facts form the basis of this second derivative test, which we will look at soon. And then we've got this definition right here that is squished very closely on this copy. We've got a definition that says a point on the curve is called an inflection point or point of inflection if f is continuous at that point, so it's got to be continuous, and the curve changes concavity from concave upward to concave downward or concave downward to concave upward at that point. So let's take a look at some examples of this. I'm just going to draw a quick sketch here of a graph. So we've got something like this. And if we've got a curve that goes through, let's say there's something like this. Well, there are points here where the curve changes concavity. So this is like concave down here, then it switches to concave up. So if this continued, there's like this concave down, then the concave up. Well, there's a point somewhere that's an inflection point. And same with this. This is concave down, then it's concave up. So concave down here, concave up. So there's some point here where you've got change of concavity. Wherever there's a change in concavity, it's an inflection point. So this is concave down, and then switches to concave up. So again, somewhere along here, there'd be some sort of inflection point.